Hello, Vanit.
Hey, Adel, how are you?
Yeah, how are you doing? It's good to hear you, man. Would you please let me see the screen sharing? Maybe you need to upload the file. Okay. Anyway,
I
you
need
could
to
upload it
share the
anytime.
screen.
Yeah, share the screen. Yeah, through sharing screen. So I'm allowing you now to. Yeah.
First of a 6-part lecture series on the topic of applications of algebraic coding theory and machine learning. Now I would like to invite Dr. Adel Ahmadi, the head of the ASA research group, to start the session. Dr. Adel.
Well, thank you, Asma. First, I would like to welcome everyone attending today in our short course in machine learning and presented by Vanit Agrawal from Purdue University. Well, let me say, some highlight about him, just to introduce him today. It's a pleasure to introduce him. He did his PhD degree at Princeton University in the state in electrical engineering, and from Princeton being graduated with a GPA 4 out of 4. This is, I think, it's a great achievement. Well, the title of his dissertation was Decision in Distributed Wireless Networks with Imprecise Information. With minors, he did his PhD degree with minors in machine learning and computational perception and computer science. Well, so his research interest includes machine learning, networking, and communications invoking algebra and coding theory. Well, he has much experience while he's still in a young age. He's leading Purdue CLAN lab. CLAN stands for Cloud Computing, Machine Learning and Networking Research. Affiliated Faculty Center of Intelligent Infrastructure, CII, with thrust lead on artificial intelligence application and other prestigious centers. Well, he is a senior member of technical staff research at the famous AT&T labs in the state. So it's a pleasure to have him today to give a short course. It's a start of a short course of 6 series of 6 lectures, seminars, lectures in machine learning, mainly in reinforcement learning type, okay? And we, as the research group of algebraic structure and applications at King Abdulaziz University, members and students, okay, try to learn such new research topics and other related topics in which algebra and its application play or may play an important roles, and build up a national research community. Hopefully we achieve that. And once again, I welcome all of you to the start of this course, and it will be 6 lectures, seminars, lectures, as scheduled in the announcement. I really appreciate and thank you very much for joining us all today from all over the kingdom, and some of you are studying overseas from Canada, from USA, and from UK. It's a pleasure to have you all here. Well, I would like now to welcome our distinguished speaker again to begin his first lecture. You can go ahead, Vanit. Thank you.
Yeah, thanks, Adel, for the invitation. And it's a great pleasure to be talking to all of you. So, as Adel mentioned, this course will be an introduction course for reinforcement learning. The key outline for this course will be, we will give a basic introduction to RL, today with what RL can do, what are its different applications, why this is a topic that is worth reading. After briefly introducing what RL can do for us, we will go into the formalism, which includes describing what a Markov decision process is. And then we will study some approaches, which are policy and value iterations. Then we'll go more focused into large-scale applications which require use of deep reinforcement learning. The key difference with deep reinforcement learning compared to the standard reinforcement learning is that we will use neural networks to scale up the state and actions, the decisions that would be needed. Finally, we will go over some applications. So some of the widespread applications that we will consider in this lecture series will be resource allocation. And in order to give examples of resource allocation, we will do a case study of ride-sharing applications like Uber, when they have to pick up passengers. So how do the vehicles operate to pick up or to match the demands of different customers? We will also study applications of reinforcement learning in communications and coding theory, where we would study how reinforcement learning can be used to find new algebraic codes for time varying scenarios. Okay.
And of course, sorry to interrupt, Manish, Vineet. If somebody have a question while you are explaining, because it's a course, it's not like a research topic we're introducing. Just we're learning from scratch, and you will go, with a reasonable speed in explanation. And if somebody has a question, I would encourage them to just ask you in the same moment while you are explaining. Is that fine with you?
Yes, that is perfect.
Thank you.
So any questions about the outline? Okay. So first, today we'll start with a brief introduction of what RL is and what it can do. So RL, I'm writing it shorthand as RL rather than the entire reinforcement learning word over and over. So reinforcement learning is learning what to do which essentially could also be said as how to map situations to actions. So if you are in a particular, so in order to understand what we are trying to say, consider chess game. So in a chess game, you have to play an opponent. So what reinforcement learning here is saying, as a player, what should you be doing? You are given a chessboard at a certain time with the opponent already have moved. How do I map this board and what I can do into perceivable actions? And my objective is, I have a reward in mind, which is in chess game, I have to win the game. So the most important thing is I have a situation, which is the chessboard. I have to do some actions and such that I maximize a reward, which is numerical. Numerical reward signal. Okay, so with reinforcement learning, we can have real decision making. For example, in a chess game, and other type of games like tic-tac-toe, which we will consider in this lecture too. So reinforcement learning is in that sense a subset of artificial intelligence, which is telling us how to make decisions in complex environments, especially time varying and dynamic scenarios. The key challenge in reinforcement learning is a trade-off between exploration and exploitation. I'll explain what these mean. Okay, so what does these mean? In order to understand what is going on in the system, I need to observe what happened in the past. In order to observe what happened in the past, I need to be able to make certain actions. So exploration is kind of exploring, if I do certain thing, what happens? Okay, so find what happens with certain actions. So I don't know the model of the system. I first need to figure out, if I moved a particular pawn, what would happen? Would it increase my chances of winning? Would it decrease my chances of winning? And things of that nature. Exploit will be, you have to see what worked in the past and then use that. So use action based on what worked in the past. So exploration is kind of going around the space and figuring out what each thing do, basically to understand the model. And exploitation is to use the learned things to make decisions. Now, if we don't explore, we don't understand anything about the system, we will not be able to exploit well. So we will be leading to suboptimal strategies. But if we explore too much, if we spend too much time in exploring, we are wasting time to learn. And also, the system may dynamically change. If you spend all the time in exploration, there's not much time left for exploitation. So that is the key trade-off in reinforcement learning, that we have to come up with the eventual signals of decision making sooner, while exploration is needed, but we have to trade off between the two aspects. Any questions so far? Okay, if not, let's go into some concrete examples. First, as I mentioned, is a chess. So a master chess player makes a move. The choice that we have to do, which is our decision play strategy, is informed by planning, which is to anticipate possible replies and counter replies. What I mean by reply is and counter replies is the actions by your opponent, and counter reply is what you do to counter the action of your opponent. As well as by immediate and intuitive judgments of desirability of particular moves. Reinforcement learning is applied a lot in robotics. In robotics, you can consider an example where you have a mobile robot at home and it is cleaning different rooms. And mobile robot also needs a charging. So a simple example could be a robot has to decide whether it goes into a new room to clean it or goes back to the charging station. So how much energy it has, it uses it to see whether it should go into a new room, but it needs to know whether how much dirt is in the new room, how much energy would be used in going into the room, and things like that. So many of you might have done undergraduate course or in control systems. So control system also is similar, where you are taking a decision at each time. So every processor control in that sense is also reinforcement learning, where you are making a decision, observing a certain state. So it has applications in most of the control process controls and other industries, petroleum refineries, and many other examples that you can come up with. I will go over two detailed applications.
Banit, I think, yeah, including me, I don't know about others. I haven't taken the control system course, but we, as a mathematician, from point of view, from background of mathematics, we were taking, like, you know, the logic. It's based on logic, I think, and probabilities to make these decisions, and it has applications in that. Here where the mathematics play rules, I think, and also, like, you know, and the judgment of distributability of, if you go back, of these machines, it should have, like, you know, some coding and programming to and through some algorithm. I think this is where the mathematics play rules, I think, because most of us, like, coming from mathematics background, so we would like to see where mathematics could play rules. I'm not sure if what I'm saying makes sense, but you could confirm it or just, like, you know, mention it somehow.
Sure. I think you said it right. So as you see in the outline, the second topic is going into Markov decision process, and many of you would have seen Markov decision processes in the probability courses. So the way we will model how to take actions will be assuming stochastic evolution of the environment and the actions you will take. And most of these systems, like the gameplay, process controls, the different resource allocations, as well as where we'll talk about design of codes, could be modeled in a sense as a Markov decision process, and that is where we will use the mathematical machinery.
Thank you, Banit. Yeah, anybody has a question, you can go ahead and ask, please, to all audience. Yeah, thank you, Banit.
Thanks. So, but does this applications kind of make sense? And intuitively look useful, why we should be studying this type of area?
Yeah, absolutely, I would say.
Okay, so I'll now go over a small state diagram of reinforcement learning, just to be a bit more precise. So reinforcement learning decision has two entities. First is an agent. Sorry, yes. First is an agent, and second is environment. So agent is the decision maker who has to take decisions. Environment is something outside which is doing certain things based on which you are making decisions. So for example, in the chess game, environment is what the other player is doing, for instance. And based on that, you get something. And agent is you as the decision maker who has to decide which element to move. So agent sees a state. State is denoted as ST. So agent sees how the environment state looks like. Based on the state, agent takes a decision, which is called an action, AT. Based on the action, the state changes. Think of state as the chessboard configuration at that time. So based on that, environment changes the state, which is fed back to ST at the next time. In addition to that, so environment gives the state for the next time, seeing the action. In addition, environment gives a reward. The reward basically says how good this action was in this particular state. So we denote the reward as RT. Okay. So this is the basic setup of the reinforcement learning, where you have an agent observing a state, taking a decision, AT, the environment updating the state, and providing a reward function. So there are four key components of reinforcement learning. They are policy. As you can understand at high level by the word, policy is the decision making of the agent. Second is reward signal, which will be related to RT. And the other concept will be value function, and the fourth concept, key concept in reinforcement learning, is model of environment. So intuitively, model of environment will have to provide ST+1. So these are the four key components that we will talk about for reinforcement learning today. And of course, in the next lecture, we will go into the mathematical details of the stochastic decision process. But today we'll keep it at the definition stage. Any questions so far before we define these four terms more formally? Okay, so we'll start at policy. So policy is mapping from states. So policy is basically how to take actions, and you are seeing the states, perceived states of the environment to actions to be taken when in those states. Note that action does not need to be, this policy does not need to be deterministic. So in some cases, policy may be a lookup table. Policy may be simple function or lookup table. Whereas in others, it may be expensive computationally. One example of expensive computation is a search process. So in general, as I mentioned, the policy may be stochastic. What I mean by stochastic is, given a particular state, the action may not always be fixed. It may be a random variable with a certain distribution depending on the state. Okay, and the key objective is to find a good policy. Any questions so far? Okay.
Yeah. So if you go back, I have a question. So in the policy, you're like mapping from the preserved states in the environment to take an action to be taken in these states. Okay, but
yes,
the action should be like, you know, taken based on what?
So as I so the agent observes a state ST and has to take an action AT. So the action has to be based on only the state, but the policy will be learned to maximize the objective, which is the reward.
Ah, okay. Just responding.
Yes. So that is why the second thing of reward signal is important, because the overall policy has an objective in mind to optimize the reward.
Let's take an example. Just a real life example to understand. We are here to learn in a simple course, okay? And
so let us do the chess game.
Yeah.
Okay.
For example, or the Uber. If you could do it in Uber, everybody's using Uber. You know.
Yeah, let's do the chess game, and Uber will do a case study in the later part of the course.
Okay, that's
okay. So in the chessboard, the state is what you are seeing, what is the current position of every player on the chessboard. Action is which element do you move, and your reward is whether you are close to winning or not, or what is the probability of winning if you take certain decisions. So you are taking, given the chessboard, you are making an action. What you move, that is policy. So you're making the decision given the state of the chessboard, and your eventual objective is winning the game. So reward is to win the game, or the probability with which you will win the game if you take certain decision. Does that make sense?
That's a good example to maximize the reward also in the policy.
Right. Okay. So as mentioned before, the second key component is the reward. The reward signal. This defines the goal. In a RL problem.
Reward signal.
So the key setup is at each time step, the environment sends reward to the agent. Reward which is a single number. So belong to R for mathematical precision. And what does agent want to do? Agent's objective is to maximize total reward it receives over a long run. So the key thing is we don't want to optimize just the instantaneous reward so that immediately you get a good reward, but we do not want to end up into a situation where later on we don't get anything. So this is basically if you are fighting with a disease, there is something, a medicine that gives you relief in the near term, but it prolongs your disease, versus it hurts you now, but gets you better in the long run. We want to prefer a medicine that makes you better in the long run, even if there are hiccups in the short term. Okay. So the key objective of reinforcement learning is not just looking now, but also looking into the future. So for example, in a chess move, there could be something you do now which may be instantaneously good, but it makes you capture your king in next 2-3 moves. We do not want to get something where immediately you are fine, but in the long term you are not fine. So in general, the reward may also not be deterministic. In general, reward function, reward signal may be stochastic functions of state of environment and actions taken. Okay, so as I mentioned, reward is the reward of a particular time. It is at each time step. But the objective is not the reward of a time step, but the total reward it receives, which takes into account the future. So in order to formalize this concept of total reward, we will go to the next definition, which is called the value function. It's very important to distinguish between reward and value. Reward is the instantaneous reward. How good would you be if you take the decision now? So if in a health condition, reward is how better would you be tomorrow, and value is considering this particular thing, how much time would it take for you to get fully better. So reward function is what is good and immediate. Value function is what is good in long term. So what I said was reward signal intuitively is what is good in immediate sense. Value function, what is good in long run. So if we have to give a informal definition, so value of a state is total reward agent can expect to accumulate in the future.
Wow.
So for example, if in chessboard you define the reward as how many. Yeah, so in chessboard, if you define reward as how many players of yours have not been killed eventually, and with a higher priority to the king, for instance, then reward is fine, but then at certain times it might be good to kill more of your pawns to get the eventual objective of winning. So value of the state, so you need to have starting from the state. So rewards could, to just reiterate, rewards could be like pleasure or pain. Values will be more refined judgment of how pleased or displeased are you in the long term.
So value of the state affected by the reward signal and value of function, right? Value function.
Yes, value function is long term. So you need to accumulate the expected over the environment and the action to see how things would change in the future. So you bring the future aspects in the value, you don't bring the future aspect in the reward. So reward is instantaneous. You get reward as a function of current state and current action. Value is based on your policy, how much reward it would, how much long-term reward would it accumulate. Okay. So the last component in reinforcement learning is model of the environment. So this is mimicking how the environment behaves. So we don't know what is the, how does the environment behaves. So a priori, we don't know what is the system model. We need to understand how the system works. So more precisely, what it does is it infers next state and reward for a given state and action. So if I have a certain chessboard, which is the given state, and I make certain move, I have to predict what my next state will be, which is I have to predict what my opponent's decision will be and how much reward would I get. So models are used for planning, which is and decision making. So the methods to solve reinforcement learning are two forms of algorithms. One is called model based. Model based, what they do is they learn the model and then make decisions based on model. This is something we might have done a lot in statistics, where we estimate the system parameters. We make assumptions of Gaussian mixture model or other things. We estimate this is how the system behaves, and then use mathematical theories to find this is what you should do in those particular environments. So this has two separate parts, which are explore first, which is to learn the model, and then exploit, which is make decisions based on the model.
So the model of the environment is just the procedure, describing the procedure of income and outcomes of the state and actions.
So given the state and action, how the next state and reward behaves. So if in a certain time you do certain chess move, how would the chessboard will be when you have to make the action next? Okay, and how good is your chess move in the current time, which is how many pawns are remaining. So the environment basically tells you, so the model is, if we are going more formally, it is, the key thing is the probability of ST plus 1 and RT given ST and AT. So this distribution is basically the environment model, which will go more formally though next time. So this is the model. If you, first option is you learn this distribution based on the past data or collected data, and then make decision assuming you know it. Model free is where you do not learn it. Do not learn the model.
And is this like a stochastic function, right? You're right.
Yes. Yeah, as I mentioned, the environment in general is stochastic. The reward distribution is stochastic. State evolution is stochastic. Okay, so these are explicitly trial and error. So you try the option, see if it works, see how well it works. You're not making a model and using the model to make decisions. And these are opposite of planning. So model based are planning based solutions, and model free are called non-planning based methods. Any questions on the different definitions? So just going back, so you have a state. The agent comes up with a policy which describes the action given the state. The environment gives you the reward of taking a particular action in a given state. So RT is a function of ST and AT. And then there is a state evolution, ST plus 1, which is also a function of ST and AT. So we studied the policy, which was relation between AT and ST. Then we studied the reward, RT. The third concept was we don't only care about RT, but the sum of RT of the future. So if we have to consider future, that's why we defined the value function. And the fourth was the policy, the environment model, which is how does the environment give you RT and ST plus 1, given ST and AT. Okay. So let us do one concrete example. We'll do a tic-tac-toe game. How many of you know what, how many of you don't know what a tic-tac-toe game is?
I don't know it.
Okay, so tic-tac-toe game is a very simple concept. You might be using by a different name. So it's a 3x3 board.
Oh,
Each
yeah.
person.
We know this very well.
Okay, so what is the name you use for it?
In Arabic, I have it in Arabic. It's not in English. I don't have it in English. But we that just like to make one line the same, right?
No, so your actions are one opponent has X, the other person has O. So if the first person plays X, the other person has to play a O somewhere. So the person who wins is the person who can create 3 X's or 3 O's in a line.
In one line, like XO game.
لا دارت تشتغل وعبير بطلت دحين صار السيارة الجنس عندنا تكفينا نحن.
Just a minute, just a minute. Let me mute all. I'll mute all. Yeah, just a minute. Yeah. Just a minute. Just mute all. Okay, and then yeah, you can speak. Yeah, you can speak.
Okay, so tic-tac-toe game is basically with this X and O. One person plays X, other person has to play O. Whoever does 3 X's or 3 O's based on their turn in a row, they could be horizontal, vertical, or diagonal, they win. Have you seen this game?
Yeah, we know it very well. Yeah, and it's called either XO game or we call it in Arabic stuffed kind of. I don't know. There are plenty of names.
Okay, yeah, this is very easy game for the kids. The only thing is, if you are an expert player, then you will never lose. Okay, so you can basically always play this game such that you never lose. Okay, we are not guaranteeing you will always win, but you can guarantee you will never lose, because if nobody can complete 3, it would end into a draw. Okay, so every skilled player can play such that they never lose. They would make it into a draw or a win. So we are not, and so we are assuming that you're not playing against a good player for understanding of our strategies. So we are assuming that our opponent is imperfect. Opponent is not very good player. It's probably a 10-year-old kid. Okay, because if our opponent is skilled, then we will never win anyway. So the problem will not make sense. Okay, so we have to basically, our opponent does not is not perfect. The opponent can make mistakes. Given that, we have to basically learn an algorithm such that we maximize our chances of winning. Okay. So we have to maximize our chances of winning in playing against an imperfect player. Now, this is, for example, a reinforcement learning problem where you have to make a certain decision. The environment essentially is to learn what does the imperfect player do. In a sense, what are the mistakes done by the other imperfect player? So there are different strategies in the past which one could say, oh, why do we need reinforcement learning? So what I will basically describe is why the different strategies are different areas do not work well. The first area I will contrast with is min-max solutions. So min-max comes from game theory. So you optimize based on the worst player. Okay. So here what you're assuming is your opponent is very, very good and you're making strategies based on that. However, if you already assume that your opponent is good, then you have no chance of winning. So you will be always conservative, and highly likely you will not win using such a model. So similarly, so basically what I'm saying is you should really understand how the other player is. Otherwise, for this particular game, for example, there is no winning strategy for the perfect player. That's why essentially min-max cannot be used. The second is evolutionary algorithms. You could use genetic algorithms and learn a policy. Even in evolutionary algorithms, you will do generate a policy space. You will be doing ascent hill climbing in the policy space, evaluate different things. So you could use different optimization methods to solve this. Even though they are good, in order to learn the solution, you have to create a perfect model of your opponent, which is model of the environment. And once you create the model of the environment and waste so much time, you could do it. So this is basically a model-based approach where you are taking too much time in learning the entire policy space. So this is definitely doable using evolutionary algorithms, but may not be a good choice because of the involved complexity. In 3x3 board, we can use evolutionary algorithms. As the board gets bigger, you will start hitting the bottlenecks in that. Okay. So to describe how we would do it using reinforcement learning, let's basically give a basic idea. If we understand this, then the formalism next time will get more easier. So we have a starting position. So you have a starting position of the board A. Let's say opponent moves first. With the opponent moves, you go to state B. Okay, so your state is captured when at this stage after you make the decision. So let us because state has to be at somebody at your point, either after you make or before you do it. So given B, then is our turn. We have many options. So many options could take us to different possible states. Okay, and let us say we choose one of them, which takes us to C, and the place where we would go intuitively, if you have value of every state here, you go to the place which maximizes the value, because value is the future reward. So ideally you would want to choose the state where your long-term reward from that state will be maximized. So I call this C or C star. C star is saying that it is optimal in terms of the value function. Then the opponent moves. You go to a state D. Then is our move. We have bunch of options. And we choose one of the options to go to E. We choose the option which maximizes the value from that state. Okay, and this keeps continuing. So as I mentioned, for us, the values are defined at these particular points. Okay, so while we are playing, the values of states will change. Some things we know. If the state, suppose we are the X player. Okay, so if you get into a state where you get 3 X's in a row, the value is 1. If you already have 3 O's in any horizontal, vertical, or diagonal positions, then the value is 0. Okay, but value from any other state of reaching into the future is not known, which we have to learn. We are learning how good a policy behaves. So in order to learn the values, what we could do is we initialize value of every state which is not the above 2 as half. Okay, we don't know whether we are winning or losing from that. We make an educated guess, which is with probability half will win. Okay, and then we have to refine it. So the way we refine it is, so eventually there are maximum of 4 or 5 moves that you can do because it's a 3x3 board. Okay, eventually from every actions that you are taking, you will reach a terminal state, which is either you get this or a draw. Okay, so draw state is value of draw is half. Is yes, neither win nor lose. Okay, so using this, you know the value at the terminal states. You have to find the value at the intermediate states, which is saying how likely are you to win from there. So the update you do, let me use the previous slide because going back is hard. So let's consider here, if I know the value of C, then I can update the value of A as the previous value of A plus alpha times value of C minus value of A. So if you take this decision, the value at a particular state will change based on how the value was in the next time. So if in C the value increased, which means C is more likely to win, then A is more likely to win. So you're making the value of A closer to value of C, that from C it is easier to win, then from A it is easier to win. If from C it is harder to win, then from A it is harder to win. So you're doing the learning rate alpha to make the previous state winning long-term probability closer to the later one. So this is the type of hill climbing or gradient descent type of thing that we will do. Based on this, we will get the estimates of values of different states. After getting the value, you will make the decision which maximizes the value of the state. So that will be the key algorithm. And if you want, you can try it in any programming language you want. to see that this algorithm will learn to win against an imperfect player, against any imperfect player. Okay, so that is basically a summary of how reinforcement learning can be used to play games against an opponent, and it will maximize the chance of winning. We will go more formalism in the next lecture. Most of the description today, if you want more details, there is a very nice textbook. This is by Sutton, Richard R. Sutton. Sorry, S. And Andrew G. Parto. The title is Reinforcement Learning: An Introduction. For more details, you can look at chapter 1 of this book. Any questions? Is the strategy at high level clear?
Well, I think to me it was fine. It's the first lecture. Of course, we need to go, and thanks for giving us some references to begin with, like the book of reinforcement learning. Just we'll go with this introduction, and I would encourage all my colleagues, all the audience, to go over it again. We'll try to provide this lecture also online, or send them the link with some access code maybe. Okay, I'll see the technician how we would upload this in our website. And I think this is the beginning. You gave us like an introduction for some terminologies and concept, so you may use it later on in details for each one, I think. So I have no question. I have asked my question and you answer me through the lecture, but I am not sure of my colleague. Anybody has a question, please? He could ask. Yeah, Asma, you could manage the questions. Yeah. So I think it seems to be there is no question from the audience. Okay. Well, I would like to thank you, Benita Agrawal, for this nice introductory lecture today. And of course, it was like, understanding the story, what's going on in machine learning, mainly in reinforcement learning, and the 4 components that will be like, discovered in more details, I think, and later on. Thank you for bringing this outlines. So I would like to ask you next lecture, what are you gonna do next lecture?
Yeah, as you see in the outline, so the next lecture we will go over formalism of these things. So we'll go over some mathematical formulation of this with the transition probabilities and all those defined, and then explain the concept of value functions, and basically the equation that I wrote will go in more detail of how to set up recursions and really find those value functions.
Well, I would encourage all my colleagues and all the attendees today to try to go over this lecture again and try to go over the first chapter of the introduction of reinforcement by Sultan and Dre. I'm not sure. I will try to purchase that book and maybe send it, like, you know, circulate the first chapter at least by email to all audience that register in this course, so they could go over it and prepare for the next lecture, which has more mathematics than today. Today is just like, you know, understanding the story and the terminologies and the concept of this course, right?
Yeah, and if you would be interested, next lecture will start with chapter 3 of the same book.
Oh, okay. Then I think I should circulate the whole book. So that's fine. You know, we're just like, you know, try to circulate this book for the sake of learning. It's like educational course. So I will send them the book. Hopefully they go over it. So they will go over the first chapter, and then they may just like take a look to the third chapter, preparing for the next lecture, right?
Yes, thank you.
Yeah. Well, thank you very much. Anybody has a question, please? It seems to be, yeah, it's a very good start, and I think it's enough for us today to digest what you have said today. Well, and thank you for this nice lecturing. You're going in a very good speed, and your handwriting is clear and understandable. Thank you so much. So we will see you all in next lecture, the second lecture of this course, which will be on Monday, next Monday. Today is July 11th, which is like, you know, 13th. Monday is 13th of July, right?
Yes.
Yeah, okay. Okay, thank you very much then. And I hope you enjoy it, guys. And see you on Monday, inshallah. Okay? Take care. Thank you. Thank you, Vanit. Very nice lecture.
Thanks.